Okay, Assalamu alaikum, brothers.
Waalaikumsalam.
So today we are going to start a new chapter, chapter 10, integrated circuit biasing. So now what is integrated circuit? Integrated circuit is all the components like resistance, capacitance, transistor, all the components are in the same base and integrated. Like your mobile phones are built by using integrated circuit. Now, when we use the integrated circuit, we need to make the integrated circuit as small as possible, and also the integrated circuit must consume less power. That means integrated circuit has some criteria. So less area, less power, and so other criteria also. So now when we use biasing in our earlier stage, we mentioned the bias, so R1 and R2. This is bias resistance. Now the question arises, why we need biasing? So biasing, why we need biasing? Because transistor, we can use this transistor as a switch or as an amplifier. So this is the characteristic curve of this BJT, and this is a load line, and we set the biasing current, that means the base current, biasing current, base current and corresponding collector current, and also VCE biasing voltage. We set the biasing voltage and current so that it is almost middle of the supply voltage, VCE divided by 2. So that if the signal, if we apply signal, input signal, then output signal also sinusoidal. There is no clipping. For proper biasing, we need to, as an amplifier, we need to place at the middle. Now, this can be done by using R1 and R2. However, for bias stability, that means when the temperature varies, our this Q point may shift it, or any variation, power supply variation, Q may be shifted. In order to reduce the shift or the variation of shift, we introduce emitter resistance. This is for bias stable, bias stable, and this one for biasing, biasing. And usually these biasing resistance R1, R2 are very high, so that these biasing resistance are not consume huge power or current. So if we need to build integrated circuit with very large resistance, requires it requires large area, because we need to draw some we call polysilicon line, and if we need to increase the resistance, then we need to increase the size for particular resistance. So therefore, it is not feasible to use this normal discrete or the resistance, huge value of resistance to build in integrated circuit. So therefore, we need to use active device. So active device to this resistance to convert to IC resistance. So this is our target. So we need to convert this resistance. Now, how to convert this resistance? So we have, in order to convert this resistance, I'll go back up. So we need to convert this resistance. So this is base to emitter, one transistor. Now, if you connect base to collector, so base and collector, then it is represent equivalent resistance. So we can mention this is equivalent. But how it happens, I'm not going through details analysis, but I can draw from the characteristic curves. This is the characteristic curves, and this is for VCE, and this is IB1, IB2, IB3, and so on. Now what happened? So when VCE1, we have IB1. When VC2, we have IB2. When we have VC3, and because this is collector voltage, and also this is base to collector, because now VBE voltage is equal to VCE voltage. So they are, so therefore, for if we, this is we can consider, because base current is related to base BB1, BB2, and BB3. When base voltage increase, base current increase, but at the same time we know the location for 0. So then this is, so that means when the VCE increase, base to emitter voltage increase, so is equal to VCE, the collector current also increase. It is almost linear. So then we can mention, then this transistor, when we connect this, it can be used as a resistor instead of using this resistance. Now for example, we can replace R1 and R2 by using this that resistance. So, but using this transistor. So instead of using this one, we can use one transistor here. And also in the bottom, we can use another transistor R2. So this is R1. This is connected. So this is R1 and this is R2. So the device size is reduced. But again, there is another RE. So, but still, if we use these two transistors, these transistors are occupied little bit area. So then it is better to avoid this resistance R1 and R2. So how to avoid this one? So now we don't add any resistance. This is our, and we can mention This is ICQ, but we don't have any resistance. So now how we can flow the current? Instead of, then we need to introduce, we can introduce as a current source ICQ. If you manage to provide this current source, which is equivalent to ICQ, and also in this case, we don't need any RE resistance also, because RE resistance reduce our voltage gain. So therefore, instead of using R1, R2, RE, we can use current source. Now our target is to design a current source. For example, integrated circuit biasing means actually we need to design current source for biasing. Now let us go. Now this is transistor, current mirror, source and sink. So when integrated circuit biasing means we need to design current mirrors, source and sink. So what is the source? Current source or mirror have three terminals. This is 1, 2, 3 terminals. The common terminal is connected to power supply or ground, and the input current source, this is input current source, input terminal is current input terminal. The output current is equal to the input current multiplied by desired gain. So this output current I out is equal to I in. So if you use a desired gain, so this is like current amplifier. The gain is unity. If the A is equal to 1, the input current is equal to output current. This is known as current mirror. So that means we need to design a current mirror so that our biasing current can flow. So now there are two types of connection. This type of connection, this is input is supplied through the supply source. This is known as source. The device is at the bottom and the device is here, and the current input is this. So this is known as sink. So now we can define that based on the connection, source and sink. Now since we are going to study this one, so current source, first we are going to study BJT current source, later on we are going to study MOSFET current source. So there are different types of current source, current sink and source. What is the function? It's maintain a constant current and attain infinite output resistance under all operating conditions. That means for ideal current source, so it will maintain same current for whatever voltage across the current source. So if it is current source, so this I out is constant, remain same without variation. This is the ideal. In this case, the output resistance of this current source is infinity. But if it's non-ideal, then there is variation with the voltage source, which is, so that means there is some parallel resistance which is not equal to infinity. So now our target is to design a current source with high output resistance. So this current source as a biasing, as I mentioned, also this current source as a load because last time in order to use load, we use RL resistance. And also the resistance is huge area. So, and more economical than resistor in IC because it use less area. So there are four types of BJT current source: the basic current source, modified current source, Wilder current source, and Wilson current source. So we are going to study one by one of this current source. Now, for example, so if I compare this one, so for example, this is my current source. Okay. So now this is my current source. Now I need to replace this RE. For the moment, I keep this R1 and R2, but I can change this one. Now this is my modified current source. Modified current source. So we have to design this current source, and this IC, now the output, this is ICQ, IC, IC, ICQ. Now we need to connect this terminal to here. So this is our open circuit. So cannot find. So this is open circuit. Now we connect. So now we know we need to design a current source to bias. So when we apply this current source, actually we don't need R1 and also R2 because this circuit supply our ICQ. Clear? So that means we don't need R1, R2, RE. And instead of these components, we replace with this current source. Now we need to design this circuit. So when we need to design this circuit, then we need to study how to design this. Design means how to find the value of R1. If you consider ideal, now in our case, we consider both transistors are ideal. Ideals means beta 1 equal to beta 2 and identical transistor. And if you look at the connection, they are connected base to emitter. So this is the ground, and in this configuration, both the transistor are BBE1 equal to BBE2. So this is base to emitter, this is grounded, and this is base to emitter, also grounded. So if they are grounded, then I can mention IB1 equal to IB. Both the transistors base current are equal. Now we know IC equal to beta into IB. So then in this case, IC1 equal to IC2 also. So now we see these are the condition for this configuration. So this configuration, now we need, so I just, instead of V naught, I just add another voltage minus VE. Now we need to find we need to design RR. That means we need to design I naught for this particular. And we need to find, so this is what is the reference current IR with, and which is the relation of output current. Now we need to find this relation in order to design. Now for this particular case, if we add KCL at this node, then so if you consider this node, this current is equal to IB1 plus IB2. This is correct because this current is equal to IB1 and IB2. So now I can write IR equal to IC1 plus IB1 plus IB2. I can also write IC1 plus 2IB1 because IB1 equal to IB2 since BB1 equal to BB2 for this particular connection. So then if it is true, then I can also change this IC1 plus 2IC1 divided by beta. So I can write IC1 divided by 1 plus 2 by beta. Correct? So now I can write IC2 1 plus 2 times beta because IC1 equal to IC2. But what is IC2? IC2 is equal to I naught. This is, now I can write. Now we have come out with the relation IC2 1 plus 2 times beta, or I naught 1 plus 2 times beta. So therefore, this is the output current which is related with IR 1 plus reference currents. So this is reference current. So this is reference current. So now we know what is the relation between I naught and IR. But how to find IR. So in order to find IR, so we need to look back to this diagram and we need to apply KVL around this loop. We need to apply KVL around this loop. If we apply KVL, then our VCC equal to I R into R1 plus BBE1 plus, no, minus, because in the bottom is negative voltage. So this is IR into R. So this is no base to emitter voltage BB1 minus VE. So from here, IR is equal to VCC plus VEE minus VBE1 divided by R1. So now these are the all design criteria. So this is one equation and this is two equation. Now if you look at, because our target is to design a current source, which and we usually prefer to design a current mirror. That means I naught equal to IR. But this equation is not equal to this. So this is, we need to design this one for ideal case, ideal mirror. But this is deviation for this circuit. And if now it depends on the beta. If beta is very high, then beta is much high, then I naught equal to IR. So now this circuit is known as basic current source. At least we can design this circuit. Now I'm giving one problem, that means design problem. So and also sometimes I ask you to draw the small signal equivalent circuit. So later on I'll draw this one. So this is the problem. So what is the problem? Design the basic current source in this figure to give the output current equal to 5 microampere. The transistor parameters are beta is given 100, VCC is 30, so this is grounded, and this both voltages are equal, which is 0.7, and also it is mentioned, so early voltage is equal to 150. So the first problem is to design the basic current source. So that means in this case, we need to find the value of R1. How to find R1? We need to find R1, because R1 we have mentioned this equal to VCC plus VE minus VE1 divided by IR. So this is VC is 30 plus 0 minus 0.7 divided by IR. But we don't know the value of IR. But we know the relation. What is the relation? IR equal to I naught 1 plus 2 divided by beta. So if we substitute, then this is 5 micro, 1 plus 2, and beta is equal to 100. And this is equal to, let me write from the answer, 5.1 micro. 5.1 microampere. Usually we prefer to IR is equal to I naught, but in this case, the little bit deviation. So now we can find R1 is equal to 29.3 divided by 5.1 micro is equal to, so 5.75 micro, 5.75 mega ohm. So now we need this value of resistance. Also, so you look at, but usually integrated circuit, this value of resistance is also very high. We don't prefer. This is the first question. And the second question is calculate the output resistance. So this, we can use the formula. So later on I'll show. this R naught is equal to, this is small signal equivalent circuit output resistance, which is VA divided by I naught, ICQ. So V naught is equal to 150 divided by ICQ is equal to 5 point, no, 5.0 micro. So if we write, the output resistance is equal to 30 mega. 30 mega ohm. Also micro mega. So now, and this is this problem, this is, and mention another problem or another statement. And calculate the collector current ratio if VCE2 is equal to 20 volt. Now how to do? Now our IC equal to, so IS e to the power base 2 emitter VT 1 plus VCE divided by VA. So if VA is not infinity, then the collector current is related to base 2 emitter voltage, also saturation current. Now if we calculate IC1 over IC2, then we can write IS e to the power BBE1 over BT 1 plus VCE1 over VA and IS, because both are same transistor, so saturation currents are same. VBE2 VT 1 plus VCE2 divided by VA. So now both are equal, VBE equal to equal. So now for this case, so now we know the relation. 1 plus VCE1 divided by VA and 1 plus VCE2 divided by VA. Now all voltages are given. So VCE 1 is equal to 1 plus, this is VBE1 and 1 plus VCE2 divided by VA. Now if we substitute, we can find. So 1 plus 0.7 divided by 150, 1 plus 20 divided by 150. So now for non-ideal transistor for early F8, so we have, so now it shows that IC1 is not equal to IC2, because in this case we have considered VA is equal to infinity. So where IC1 equal to IC2, but when we consider VA is not equal to, but we can see there is some deviation. IC1 equal to not IC2. So this is 20. Now if I ask you to draw the small signal equivalent circuit, I just draw very quickly. So what I can do, as I mentioned, so this is supposed to be ground, Then base 2 emitter, there is R pi 1, and this is R pi 2, and collector to emitter we have, so G, or I can write in terms of beta 2 IB2, and also output 0, and also this is same, so beta 1 IB1, so R01 R02. So this is our equivalent circuit diagram. Then after that we need to remove these inside components. So inside components. So this is. So no, base. So this is. So now if I copy it from my slide. So this is a, but what is that circuit diagram? So if we redrawn, it is not necessary to rearrange. So it's supposed to be look like this. So this is I naught. So but we are not going to find the output resistance. So in order to find output resistance, then we need to apply Vx, turn off all independent icon. But this output equal to approximately equal to R02 is equal to R01. So just we use this formula, final formula, which is VA is equal to I naught. So this is the basic current source. Okay. Now before going to modified current source, I need to mention that. So I am going to take one quiz on next Tuesday. Next Tuesday, 16th, probably the 16th. And this is the high frequency. High frequency, we have studied short circuit current gain, short circuit current gain, and Miller effect. And this quiz, so because I'm going to take both the section together, so I'm going to conduct from 10 p.m. So the quiz. So now you note it down. So on Tuesday there will be no morning class, and it will be held on 1 p.m. And after that I will mention during the quiz time. So now we have finished the first out of 4 configuration 1. So basic current source. But this basic current source has mentioned this is not close to the ideal mirror. So then we need to modify this basic current source. So what is the modified circuit? Now I can bring from my slide instead of drawing. So modified current source. So now in this case, we have added, so instead of this base 2 emitter, we modify in between, we add another transistor. And also I just make it more generalized. I make it, this is minus VE. In my previous case, I not equal to IR, which is 2 1 plus 2 times beta. So that means I naught is not equal to IR. So there is some variation. So now if we modify, then this modified is close to, very close to this. Now we need to verify this. Now again, we need to design this current source. So design means we need to find what is the value of R1. So first we need to calculate what is the value of R1. So again, in order to find R1, so this is our VCC. So we need to apply KCL up to the ground, up to the next source. Now, if you apply KCL, then I can write KCL, VCC is equal to IR R1 plus BBE3 plus BB1 minus VE. Now from this equation, I can find R1 equal to VCC plus VE minus, so previously only BB1, now we have BBE3, so divided by IR. So now we have additional voltage because of Q3. Now in this case also we need to find the relation between IR and I naught, or we need to find I naught as a function of reference current. So we need to find the relation between I naught and IR. Then can solve this one, brother? Can do, or I need to show you? Brother, I need to show you, or you can do? Can or cannot? I need to show. Show us, sir. Okay, thank you. Then I need to show. So now, so now this is our modified. I need to show you how to do. Now I just copy to another clean place so that I can see the diagram. Paste. Now I need to apply KCL at here. Now if I apply KCL, then I have IR is equal to IB3 plus IC1. So now we know. So last time we have IB1 plus IB2, this. Now if we look at this notation, then IE3 is equal to IB1 plus IB2. Correct? So now we apply KCL. IR is equal to this current plus this current. Then IE3 equal to IB1 plus. Now this IB3 is related to IE3 because last time we have easy to find. Now because of this, now this is what is the relation between. Now we also know IE equal to 1 plus beta times IC, right? We know or we don't know? We know. So then, and also I is equal to 1 plus beta IC. And also I can write 1 plus beta times IC equal to beta times IB. So we know because IC is equal to beta times IB. Now I can find the relation between, and also IE3 is equal to 2 IB1 because as I mentioned, BBE1 equal to BBE2, therefore IB1 equal to IB2. So now we know the relation between this one. So that means IE3 equal to 1 plus beta. So beta times IB3. So then, so then IB3, I can write IB3 is equal to IE3 divided by beta 1 plus beta. So now again, what is IE3? IE3 we have mentioned beta times 1 plus beta 2 times IB1 because IE3 is equal to 2 times IB1. Now we convert this one to IC1. So now we can write something is wrong somewhere. Let me, okay, later on we can dig out what is the wrong. So okay. So now we substitute our IR is equal to IB3 plus IC1. Oh, it's okay. So then this is IB1 is equal to, so IB3 is equal to 2 IB1 divided by beta 1 plus beta plus IC1. Something is somewhere is wrong. So what is IB1? IB1 is equal to IC1 divided by beta 1 plus beta plus IC1. So this is IC1 2 divided by beta square plus there is not matching with the text. So this is supposed to be 1 beta is x. Okay, instead of writing something is wrong somewhere. Can you identify, brother? 1 plus beta, 1 plus beta. Check. There is somewhere is wrong somewhere. Just okay, just try to remove this one because something is wrong somewhere. So I can write I can write IC. So now this is up to here is okay. Now I can write this is this is IC. Then IE3, IB1. Then what is the relation between IE3? Can solve or cannot?
The IE1 is 1 plus beta times IB.
Oh, yes, you're right. So this is the wrong, is it right? Yeah, this is now I wrote the wrong formulation here, correct? It's supposed to be not IC, it's supposed to be IB. If it's IB, then IE3 equal to 1 plus beta times IB3. Now correct. So then IB3 equal to so now IE3 is equal to how much? IE3 is equal to 2IB1 is equal to 1 plus beta IB3. So therefore, IB3 equal to 2IB divided by 1 plus beta. Now matching my, now substitute IB3 is equal to IB1 divided by 1 plus beta plus IC1. So is equal to 2 IC1 divided by beta 1 plus beta plus IC1. So I can write 1 plus 2 beta 1 plus beta IC1, which is equal to IC2, which is equal to I naught. So therefore, I naught equal to IR 1 plus 2 times beta 1 plus beta. So now we come out with the final relationship. So in this case, so we have another 1 plus beta. So in this case, it is very close to IR because 2 divided by beta, initially 2 divided by beta, now become 2 divided by beta 1 plus beta. So that whole product is now become very large. So then it is, so if for this particular case also if we are not going to derive R naught equal to R0, which is VA equal to IA. Now let us do some exercise for this case and see. Same. So this is the circuit, and we need to do the same problem. So now we can find this R1 is equal to VCC minus BBE3 minus BBE1 divided by R1. This is the relation 1. Another relation, IR is equal to I naught. So IR is equal to I naught 1 plus 2 beta times 1 plus beta. So in this case, if we substitute I naught, then we can find this is equal to also 5 microampere. Previously, we got 5.1 micro. So this is this is very close to 5 micro. So IR is equal to I naught. So, and also similarly, we can find this one. We know. And what is the relation for the second one? IC1 over IC2. Then 1 plus VCE1 divided by VA, 1 plus VC2 divided by VA. So now, last time, in previous case, VC1 equal to BBE1. But this case, BBE1, VCE1 is equal to how much? So this is VCE1. Then we need to apply KVL. So for KVL, then VCE1 equal to BBE1 plus VBE1 3 plus BBE1. So in this case, VCE1, because previously it is connected. So connected VCE1 equal to VBE1. Now in between, now we apply KVL. So now this is the difference between two difference. One is this 3 difference, VCE1. This is difference, and this is 3 difference. So now we have studied two configuration. So this is today is up to here. So what you after that I'll go to upload to Classroom, and also I try to make this video to upload to YouTube. Any question? No. If not, then we can finish our lecture with recitation of Surah Al-Asr. Okay. Assalamu alaikum.